speaker Alessio Martini from Politecnico di Torino. The title of his seminar is Sharp LP Estimates for the sub-Riemannian wave equation. With this, I would like to invite him to deliver his talk, and I also request all the participants to mute their microphones. Over to you, Alessio. Thank you.
Thank you very much, Una, and thank you for the kind invitation. It's a great pleasure and honor to have the opportunity to deliver this talk in this seminar. So this is an opportunity for me to present some of the work I've been doing. It's joint work with Detlef Müller from the University of Kiel in Germany. And this is the problem we have studied is trying to obtain sharp LP estimates with loss of derivatives for the sub-Riemannian wave equation. So it's a wave equation driven by a sub-elliptic Laplacian or sub-Laplacian in certain geometric contexts. So I would like first to try and introduce the general problem I'm going to talk about also in the RD case or anyway the model case, and then see what changes when we move from, say, the standard Laplacian to more general sub-Riemannian settings. So the general problem we can see like this. So think of having a Laplacian L. For me, L will denote a positive definite Laplacian or some variant thereof on a geometric context. We know that if we form the cosine family associated with the square root of the Laplacian, we can think of it as a self-adjoint, positive self-adjoint operator, we get an object which is sometimes called the wave propagator, which can be used indeed to express the solution of the initial value problem for the wave equation. So here I have the wave equation driven by the Laplacian with the initial datum at time 0, which is f, and we assume that their time derivative at time 0 is just 0, and then we can use the cosine family representation for the solution. Of course, one could also specify a different value for the time derivative and would also need to introduce the sine family, but just for simplicity in this talk, I just stick to the case of the cosine family here. Okay, so when we have the solution represented like this, one question that one may ask is what conditions one may impose on the initial datum f in order to ensure that the solution at a fixed time t, for at least for small time, remains in LP. So for example, if the initial datum is in LP, can we ensure that then the solution is in LP as well for a certain amount of time? And the fact is that while for p equals 2, this is trivially true in the sense that the cosine family is actually a family of contraction on L2. As soon as we move away from p equals 2, then the problem is become trickier. So for example, in RD for d greater than 1, this is no longer an LP bounded operator for p different from 2. And one way to sort of fix this is to add this factor here, composing the wave propagator with this kind of decaying factor in terms of the spectral calculus of the Laplacian, which essentially can be interpreted with the fact that if you want your solution to stay in LP, then you need to require the initial datum not only to be in LP, but also some derivative of certain order, and the order of the differentiation is this parameter S, and we ask also that these are in LP as well. And so then the question may become, for a given P, what is the sharp range of parameters S for which this estimate holds? Now, as I mentioned, when p is equal to 2, you can just take s equal to 0, or any s larger than 0 would also work. So somehow, because this problem is sort of self-adjoint, we can actually restrict to the case p equal, so p less than 2, and so the other endpoint it would be just p equals 1. Now, so let's have a look at the case p equals 1. And one first observation is that by appropriate dyadic decomposition, one can effectively reduce the problem to studying a spectrally localized version of the cosine family of the wave propagator. So we introduce a spectral cutoff, chi1 applied to the operator, and then the problem becomes bounding this L1 operator norm of the spectrally localized portion of the wave propagator in terms of the power of lambda, and see what the power is, I mean, as lambda, when lambda is large, so as lambda tends to infinity. So as up to epsilon losses, one can see that in the exponent s, one can see that these two estimates are essentially equivalent. And so now, just to get an idea of what to expect for this problem, for example, in the case of the Laplacian, standard Laplacian on RD, well, in this context, by scaling translation invariance, what one can see is that the problem reduces to bounding the L1 norm of the convolution kernel of this operator at time 1. And so here we're just studying effectively the cosine family applied to this sort of spectral localization kernel, which is just a Schwarz function in the case of RD, and effectively it's actually a rescaled version for with the parameter lambda, scaling parameter lambda.
So what is
over
delta
fixed.
0 here?
Sorry, it's just this delta distribution at the identity at 0.
Okay,
yes,
delta.
at the origin. Yes, so that gives you the convolution kernel of the original operator. Yes, so now this, I mean, in RD you just work it out by the Fourier transform. This is just a Schwarz function, and it's just a scaled version of the same Schwarz function with a scaling parameter. And by sort of simple computations, you can see that then the LP norm of this guy is just an appropriate power of the scaling parameter. So now what happens is that we are effectively applying the cosine, the wave propagator at time 1 to this guy. Heuristically, we could think of that this initial cutoff up to sort of Schwarz tails is effectively supported in a small ball of radius lambda to the -1, and because lambda here is large, when we apply the cosine family, so the wave propagator at time 1, what we expect is that by finite propagation speed, the support of the result, again up to negligible Schwarz tails, should be contained in a ball of radius, the initial radius plus 1, which is the time. So since lambda is large, then this ball is still of a fixed radius effective. So everything lives in a ball of radius comparable to 1. And again, of course, you have to take care of the Schwarz tails, but if you do that, then by sort of assuming that you can just neglect the tails and so everything really lives in this ball, in order to estimate the L1 norm of this guy, you can just use Cauchy-Schwarz and estimate it with the L2 norm because everything lives in the same ball. And then you just use the contractive property of the cosine family to just remove the wave propagator, and this norm we just know how to bound in terms of scaling considerations. And so you see we get this d/2 exponent, and these heuristics can actually be made precise, and one can see that in RD this exponent d/2 is a good exponent for this estimate. But the fact is that this is not a sharp exponent. One can do better, but requires somehow more sophisticated heuristic. So the point is that here we could think of the fact, and this is what I label Sharp-Huygens principle, perhaps a bit inappropriately, but the idea is that actually the main part of the solution will not live in the full ball, but only around the sphere, so the boundary, which is the idea of the fact that the singular support of the wave propagator is actually this wave front is just the sphere center at the origin, if you start with the starting point at the origin. And so if you now take this heuristic into consideration, that the annulus has a smaller volume than the full ball, you can gain a power of lambda to the -1/2 when you apply Cauchy-Schwarz, and then
I have a small question
yes,
here.
Please.
The thing is, you are bothered about to finding S and P also, right?
Yes.
So what it is, all the things you are doing for P is equal to 1, or doesn't matter actually?
As I mentioned, for P equals 2, this is trivial. You can just take S equals to 0. Yes. And so any S bigger than 0 because of it's just a contraction in L2. It's a self-adjoint problem. So working for P less than 2 or P bigger than 2, you just reduce problems to duality. So effectively by taking adjoints. So effectively you can work for P less than 2. And then the idea is that if you understand P equals 1, at least for sure you can interpolate. And
so
at least in the case of RD, it turns out that the interpolation estimate is actually the sharp one. You cannot do anything better than interpolation as soon as you get the sharp estimate for P equals 1.
Basically, this will for every P actually.
So at the end of the day, by interpolation, you can then recover the intermediate P's, and you will have intermediate exponents. Yes, exactly. Which goes from 0 to this d-1/2 when P goes from 2 to 1 or from 2 to infinity, effectively. That's the idea. Okay. So this is what we are getting here. And so d-1/2 is the sort of exponent we get. This is only heuristics, but effectively, as it turns out, these heuristics can be made precise with a certain amount of work. And this is what leads to what are often known as Miyachi-Peral estimate for the wave propagator. Okay, actually, the work by Miyachi and Peral are even deeper than this, because I think that the result that I mentioned it now with this notation for the spectrally localized version of the cosine family and with potential epsilon exponent, epsilon losses in the exponent, I mean. So in the non-endpoint result was known earlier. There is some work by Sjöstrand on that. But what Miyachi and Peral did, and that's why I put the names in red, is actually to get some endpoint estimate for the exact value of the exponent. To be precise, actually, you can even get a non-spectral localized estimate at the endpoint, but there you need to replace L1 with some Hardy spaces or BMO in the case of L infinity, if you wanted the exponent which to be d-1 and not d-1 plus epsilon. Anyway, so that's what they did. And this, of course, is the result for the Laplacian on RD. But one may ask, what happens or more general situation, geometric settings? The Laplacian is a local model for more general elliptic operators of manifold, like the Laplace-Beltrami operator on a Riemannian manifold. And as it turns out, at least locally, the result can be reproduced in this non-constant coefficient setup. For example, there is a deep result by Seeger, Sogge and Stein, which follows from their annals paper in 1991, that tells us that actually for the Laplace-Beltrami operator on a compact Riemannian manifold, you can study the same problem and you get exactly the same kind of estimate with the endpoint ones, with the exponent being related to the dimension d of the underlying manifold. Okay, so their work actually is much deeper in the sense that they require more sophisticated representation of the wave propagator in terms of FIOs. This was actually known before, but what they do is that as soon as you have this kind of FIO representation, then you apply their machinery that gives you some appropriate LP bounds for certain classes of Fourier integral operators, which then lead to this kind of estimates. Okay, so we do have a quite clear understanding of these Miyachi-Peral estimates in, say, the elliptic setting, at least when we have a compact manifold. Of course, if you might ask what about more complicated geometries at infinity, which are not just compact. And actually, if you have are not really interested in the sharp exponent, but just to know that some exponent exists, actually there are much more general results that you can apply. And there is actually a relation of this problem, wave equation estimates, with the LP spectral multiplier problems, which have been proved in a quite great generality. For example, for operators which satisfy Gaussian type with kernel bounds on a certain doubling metric measure space, so the underlying geometry is doubling. You have a certain dimensional parameter associated with the underlying geometry, and then there are quite general spectral multiplier results, which imply that the Miyachi-Peral estimate in that setting holds with an exponent which the sharp one, is at most q over 2, where q is the dimension. Now, this result is not sharp even in the elliptic setting, because in that case, q would be equal to d. And so you are missing a 1/2. Sort of you're losing a 1/2 in the exponent, but it's already almost there in a sense asymptotically. The fact is that, interestingly enough, these results about spectral multipliers actually hold also in situations where the Laplacian type operator that we are using need not be an elliptic operator, but may just be sub-elliptic. And this is the setting I want to talk about today, which is of sub-Laplacians and sub-Riemannian manifold. Now, one important observation in this context is that actually, when the operator is sub-elliptic, normally the dimensional parameter associated with the underlying geometry, which describes the volume growth of balls and so on, is normally strictly larger than the topological dimension of the manifold. And this is related to the lack of ellipticity of the operator itself. Now, just to make the simplest possible example of what we're going to talk about is that of the Heisenberg group, which most of you will know very well, is say the smallest Heisenberg group as a manifold. This is just R3. I write it as R2 cross R with the variables x and u. The dimension of the manifold is 3, but as we shall see, the sort of dimension associated with the underlying geometry, the sub-Riemannian geometry, actually this homogeneous dimension will be 4. So it's something larger here we put this polynomial group law, and we then form the sub-Laplacian by taking a sum of squares of two left invariant vector fields appropriately chosen, in which at the origin are in the directions of this x factor. And now, as it happens, this operator is not elliptic, because if you freeze the coefficients, you only see a partial Laplacians in a certain pair of direction, not the full three sort of dimensional situation that we have in the 3D manifold. But these two vector fields which form the sub-Laplacian are bracket generating. And so that's why by Hermander's classical theorem, this operator, despite not being elliptic, is sub-elliptic. And so somehow enters into the discussion today. Well, one can write this operator in terms of its principal symbol, which can be written in this form. And here you see I have the point, and then you have the sort of frequency variable, which you can think of as an sort of a covector in the so in a sense, this principal symbol you can think of as a quadratic form on the cotangent bundle of our manifold. Now, I wanted to a little bit to talk about the geometry, which is associated with this Heisenberg group sub-Laplacian, because, I mean, the idea is that geometrically waves propagate along geodesics. And I mean, in the case of RD, these are just straight lines, so the wavefronts become balls. But in the Heisenberg group, things are much more complicated. And see how to get the right geometry associated with the sub-Laplacian. The idea is that when you think of curves, that join one point to the other in the Heisenberg group, only those which are horizontal are allowed, meaning curves whose tangent vector is in the span of these two vector fields. So at every point, you can only move in a two-dimensional set of directions, but this plane to which the horizontal curve might be tangent to changes and tilts if you move from one point to the other. And this is why if you start from the origin, maybe you cannot move directly upwards to join any other point of the u-axis, but if you move a bit outside, then the plane tilts, and then you can move upwards, and then you can just start spiraling and doing a movement like that. And this way, even if you cannot directly go upwards, you still can join any point with any other point on the Heisenberg group by horizontal curves. Then you can make sense of then a distance associated to this sub-Laplacian, taking the infimum of all lengths of horizontal curves joining one point to the other. This is what is called Carnot-Caratodori or sub-Riemannian distance on this setting. And actually, even in this setting, you can speak of geodesics that we know are relevant to this discussion of wave propagation. And we can even make sense of the geodesic flow, much as on Riemannian manifolds. Here, it's convenient to set up the problem by using the principal symbol of the operator as a Hamiltonian function on the cotangent bundle, define a Hamilton flow, and then projecting this flow onto the manifold, giving you the geodesic flow, so a flow made of locally length minimizing curves. What is different in this setting compared to the Riemannian or elliptic case is the fact that from one point, you might have different geodesics which leave the same point with the same initial tangent vector, but parameterized by a different tangent covector. And you see that these curves leave with the same tangent vector at the initial point, and then start spiraling if you take a steeper and steeper initial covector here. And you see that then you get these very much more complicated locally length minimizing curves in this setting. So this is what would be the analog in the case of RD of taking rays emanating from the origin. Now, if you stop this flow at time 1 and you take the endpoint, in the RD case, you would just get a sphere of radius 1. In this case, if you join all the endpoints of these curves, what you get is this kind of very complicated profile, which you can think of the geodesic sphere or the wavefront in the Heisenberg group. And so you see this kind of equatorial region, which somehow is much more similar to the elliptic or Euclidean case, the standard sphere, but these infinitely many zigzags that you have here around the axis make the sort of study of fine properties of wave propagation much more complicated. And I mean, this may already seem complicated, and there's some intrinsic difficulty that you have to sort of tackle when you are studying the wave propagation in this setting. But this, in a sense, of the Heisenberg group is actually the simplest possible situation that you might want to study in this context, because I mean, what we have seen is just the smallest three-dimensional isotropic Heisenberg group, and this might be a picture of a portion of this wavefront set with this infinitely many zigzags. But if you take higher dimensional Heisenberg groups, you can also change the coefficients in front of the vector fields from in a sub-Laplacian, and you get what are known as anisotropic Heisenberg groups. And the shape of this object changes even, it becomes even more complicated because you do not have any symmetries anymore. And these, again, are still quite simple situations on the Heisenberg group, because then you could also think of taking even just the simple idea of taking the direct product of the Heisenberg group with R, and the pictures that you would get are even different. So it's just to say that the difficulties you might have to face when you study wave propagation in this setting are much more complicated than what you would get by looking locally at what happens on a Riemannian manifold, where these things would just be spheres or diffeomorphic to spheres at most scales. Okay. So this is just to give you an idea of the kind of objects that one needs to study in this context. And well, one thing that we have established relatively recently in collaboration with Detlef Müller and Sebastiano Nicolucci-Golo is that in this setting, for any sub-Laplacian or any sub-Riemannian manifold, for sure you have a necessary condition for the validity of these Miyachi-Peral estimates for the wave equation. So you cannot do anything better than what you would do on RD for the elliptic situation, where D is the topological dimension of the manifold. And this one, which might seem okay, I mean, considering that the homogeneous dimension is large, it might not seem necessarily the best lower bound. Actually, it's not a trivial result to obtain, I believe, because in a sense, if you look just of the sub-Laplacian, as we know, this is just a partial Laplacian when you freeze the coefficient. So if you just use some standard perturbation techniques to relate the problem on a manifold to the problem on a D, actually you would only see a few directions. And so the trivial lower bound, the necessary condition, would only involve the dimension of the horizontal distribution and not the full dimension of the manifold. So the fact that we can get the full dimension here is already indicating that this topological dimension has something to do with the problem. But then there is also a sufficient condition which is known, so an upper bound on this sharp exponent, which is given by the fact that in a number of situations for special distinguished sub-Laplacian Heisenberg groups, Heisenberg type groups, variations thereof in many different settings, with when some symmetries at least are available, one can often prove an improvement of this result I mentioned before about spectral multipliers, replacing the homogeneous dimension with a topological dimension, so pushing down this condition. And so, at least in this setting, now we see that the gap has now become small. I mean, the question now remains, can we do better, and can we even get to the d-1/2? But even in these many settings where we know this upper bound d/2, I would say very few results about what actually the value of the sharp threshold are known so far. One classical result that has been known for a while now is by Müller and Stein, and they work in the context of the Heisenberg group we've seen before, and prove that indeed we can get to d-1/2, like in the Euclidean case. This has more recently been improved by Müller and Seeger, who considered a more general class of groups we called Heisenberg type groups. In this setting, we can get essentially the same result and even a better one, because they also get some endpoint estimates of RD and BMO type. But one of the drawbacks of the method that they use, quite fundamental one, I mean, of course, it's very nice because you get very sharp results. A potential drawback of the method is the fact that these methods are very specific to the setup that we are working with. And so in particular, they use a lot of information from the representation theory of these groups, the fact that you get you use, for example, Miller type formula for the Schrödinger propagator in the context of Heisenberg and Heisenberg type group. You use this kind of radiality I mentioned before. And so a lot of these kind of symmetries are used, and it's not clear how to use these methods in a more general, robust perturbed context where you may not have all these symmetries. For example, the anisotropic Heisenberg groups are not included in the Heisenberg type class that Müller and Seeger consider. Well, what we could recently show with Detlef is actually that we can develop an alternative method, which is more in the spirit of the method by Seeger, Sogge and Stein, so developing an FIO representation for the wave propagator that indeed allows us to get a sharp LP estimates with loss of derivatives in this context, and actually in an even more general class of groups, which are not just Heisenberg or Heisenberg type, what are called Métivier groups, which I won't now enter immediately in the definition of that. If I have time, I'll tell you something later. But for example, let me just mention that the Métivier class includes the non-isotropic Heisenberg groups I mentioned before, whereas Heisenberg type does not. And actually, more recently, we also managed to adapt our method to consider direct products of Heisenberg groups or direct products of Heisenberg and Euclidean spaces. So somehow a more robust method, more based on the underlying geometry by using an FIO representation for the wave propagator that indeed allows us to get the result. Somehow a limitation of our current approach is that we miss the endpoint. But I think that it's actually a good thing that we didn't aim for the endpoint immediately, because this would have sort of made the problem even more difficult. Whereas I think now it's more a phase of discovery of a different approach and method that hopefully will, in the long term, also allow us to treat also perturbations of this object, and so have a somehow more general approach, which again has the same kind of robustness as we may expect, for example, in the case of the elliptic situation for compact manifold. Okay, so this is somehow at least gives you the framework when you're working with, and a presentation of the result. And now in the remaining time, I would like to tell you some ideas from the proof of the result. So in order to do that, it may be convenient for me first to recall what the Seeger-Sogge-Stein method is, even in the simplest case of the Laplacian RD, because then it's essentially the basic tool that will be then used in many other places in our approach later. So we work in the Euclidean setting, so for the standard Laplacian RD. And then we know just by using the Fourier transform that we can represent the cosine families of the wave propagator in terms of an oscillatory integral operator and FIO with this very explicit phase function, which involves this linear part in psi, which is just coming from taking the Fourier transform and the inverse Fourier transform, and this T mod of psi, which just comes from the symbol of T square root of the Laplacian. We are by scaling, which can assume time being 1, and we introduce the spectral localization that we know we want to consider, which in this case is just the frequency localization in the FIO representation. So we just add this cutoff, which tells us that mod of psi should be about lambda. So effectively, we are working in this annular region where mod of psi is about this spectral parameter lambda. And the key idea in the Seeger-Sogge-Stein argument, one of the key ideas at least, which is what I want to talk about now, is the fact that we can further decompose this sort of annular region into angular thin spectors of an appropriate aperture. So effectively, after this additional splitting, this second dyadic decomposition, sometimes it is called, you get that the new amplitude after introducing an appropriate cutoff is supported in a certain tube of a fixed direction of sizes lambda and lambda to the 1/2 in a fixed direction psi naught. And now, as it happens, this kind of localization allows you to linearize effectively the phase. So the new phase, you can replace this mod of psi with some term which is linear in psi, where this direction psi naught of the tube appears. And now this with the linearized phase, what happens is that you are just doing a modulation in frequency, which corresponds to a translation in space. So geometrically, what happens is you take the dual box corresponding to this tube, and then you apply this translation, that is a translation of sort of length 1 in a direction of the tube. So you get this Planck going to the sphere. You do the same for all of these tubes, and you see that as the result, you obtain this thin annulus. This is exactly what we got in the previous geometric heuristics we mentioned before. So this is just to say that this kind of dyadic decomposition, second dyadic decomposition corresponds, and is a way of making precise the heuristics that we discussed earlier. And actually what one can see by appropriate computations is that each of these pieces gives a unit contribution to that one operator norm. So the resulting operator norm can just be bounded by triangle inequality by counting the pieces. And if you do the appropriate counting, you get the power d -1/2, which is what we expected. So it's just to say in a nutshell what one of the key arguments in this Seeger Sogge and Stein method is. And this is what we would like to use also in later steps of our proof. So just to mention that this kind of argument can be extended to and applied also to the setting of elliptic operators, second order operators like Laplace-Beltrami operator, at least on a compact manifold. Because as it turns out, also these operators can be written in terms of their principal symbol plus our other terms. And one can obtain an FIO representation, this is a classical result, of at least locally and for small times and up to smoothing terms of the wave propagator in this setting. And now the phase function and the amplitude are no longer explicit, but can be constructed by nowadays classical argument. One way is to take a phase function that satisfies the iconal equation associated with the principal symbol, and then solve appropriate transport equations to actually obtain the appropriate expression for the corresponding amplitude. There are different possible choices for the phase function. One popular choice in this context is the one by Hermander that shows that one can take a phase function which is the sum of a term which is independent of time plus something which is t times the square root of the symbol. In the case, Euclidean case, it would just be t mod of psi. And this other part is just a perturbation of the linear part inside that we have seen before. So this is just to mention that by this kind of consideration, one may believe that effectively, at least locally for small times, one can repeat exactly what we've done in RD case to get a similar estimate also on the manifold situation. And compactness allows one to localize the problem of finite number of coordinate patches. You can do kind of this representation. And that's why, at least on compact manifold for small times, you can get exactly the same kind of behavior. But as I mentioned before, this is also clear, at least at a heuristic level, geometrically, because the geometry locally in a compact manifold, when the operator that drives the propagation is elliptic, is essentially the same. The wavefronts are diffeomorphic to spheres, geodesics are like rays emanating from a point, and so you don't really see very much when you look at small times the difference from working in RD. But as we know, in the sub-Riemannian setting, for example, in the Heisenberg group, things change considerably. So what should we do then? Well, these pictures sort of motivate the fact that indeed we have quite a different situation in that setting. So, well, let me just tell you something about the Heisenberg group case. Well, our aim is to obtain this spectrally localized version of for sort of estimate for the L1 norm of the wave propagator. Here I put a double twiddle to mean that I admit epsilon losses in the exponent, so I just want to avoid the cumbersome notation for that. Because we are in a group invariant setting, you also have some appropriate scalings available. We can actually reduce the problem to the time one problem and to working with the convolution kern. So again, here we have the delta at the identity that can be used to write the convolution kern. And now, much as in the initial heuristic I showed you, by finite propagation speed, one can actually see that outside the ball, a sub-Riemannian ball of radius, say 2, something larger than 1, we have negligible tails, and so we can localize the problem in space. And now the problem is how to get this kind of estimate. Since we aim for a FIO approach, it would be convenient also to know where frequencies are localized and how to relate the spectral localization with the frequency, more standard frequency localization here. And in the Euclidean case, it was just trivial. We know that square root of L correspond to mod of psi and frequency space, but for a sub-Laplacian, this is no longer true. So what we do is to introduce an additional dyadic decomposition in frequencies, and we do this independently into the dual variable psi and mu or to x and u. And then we have to see which of these frequency regions are actually relevant, how to relate the lambda parameter with these parameters 2 to the j to the k that correspond to the frequency localizations. From scaling arguments, one can actually show that at least at any heuristic level, one would expect that this psi should scale like lambda, whereas mu should scale like lambda squared. And indeed, one can make this precise and show that outside this union of these two regions, A and B, the rest is given by negligible contribution. So either psi is about lambda and mu is less than lambda squared, or conversely, mu is about lambda squared and psi is less than lambda. And now, in order to get an understanding of what we are studying here, it may be useful to compare this frequency localization with the wavefront that we had a picture before, in the sense that we can look at the geodesics whose initial covector lies in one of these two frequency regions and see what the endpoint comes up. And for the A region here, where mu is about lambda squared, you see that actually you have all these infinitely many zigzags that appear. But this spatially is very, very much more localized compared to the rest of the wavefront. And so thanks to this additional spatial localization, we can take advantage of this and use much easier sort of approach to take care of this region, more in the, like in the original heuristic, like with Cauchy-Schwarz, more or less that's it. And so effectively the interesting region is more the blue one. And for technical reasons, we further split this into a smaller part, which is in green here, which is the elliptic region, because in that part, actually the principal symbol is effectively an elliptic symbol for which more standard approaches can be used. So the truly interesting part now remains this blue region, the non-elliptic part of this frequency region. So how to deal with that? Well, there are a number of steps in the proof. First of all, well, we have this kind of spectral localizations where we have two different possible values of the localization in psi and mu. One is 2 to the j and one is 2 to the k. They might have quite different values. So it may be convenient to reduce to something which is more isotropic. We can do this by using parabolic scaling, which is available on the Heisenberg group setting. But the consequence of that is that if you apply a parabolic scaling, the result is that we can reduce to a more isotropic frequency localization, but you also have to rescale space and also rescale time in the estimate. So at the end of the day, you can reduce to a more isotropic frequency localization at the cost of studying estimate for large time. And this is somehow an additional difficulty that was not apparent in the Euclidean or elliptic setting, where actually studying problems just for small time was completely enough. And we needed to find a different way, because there are somehow topological obstructions to applying the standard FIO representation for the wave propagator if you want to work with large time in the presence of caustic points in the geodesic flow. And so we were somehow lucky to discover that at least in the elliptic setting, someone had already thought about this problem and obtained a somehow global in time and space FIO representation for the wave propagator, so for elliptic Laplacians. But the idea is that here you need to use a complex valued phase function. And so what we could do by adapting this work by Laplace, and Vassiliev to our setting, so they did something in the elliptic setting. What we did is to adapt this to the setting of the Heisenberg group, so in the sub-Riemannian situation. And we could show that actually in this setting, one can make this approach work. Okay, so we can express very explicitly the phase function in this representation in terms of the geodesic flow. This phase function is different, is complex value, doesn't satisfy the iconal equation as before, only on the singular set. We have this additional density term, which somehow makes the representation global. And we have an amplitude which corresponds to this frequency localization terms plus lower order terms, which are obtained by solving appropriately certain transport equations. So one crucial step in our proof is showing that this representation in the case of Heisenberg-related groups does not blow up in time. This was not contained in the work by Lapton, Sapolov, Vasiliev, who were more interested in obtaining some representation up to smoothing terms, but without uniform bounds in time or something like that. And we had to work this out explicitly in the case of the Heisenberg group or other groups that we consider. We have some blow up in the density, but this is under control. And at least for small time, this representation is perfectly fine to be used for applying the Seeger-Sogge and Stein approach with some modifications taking into consideration the imaginary part of the phase function. And in the end, you get the appropriate estimate. What really remains, however, as I mentioned before, the main difficulty remains what to do with large times. And the challenge here is that in order to apply the Seeger-Sogge and Stein method, you need to differentiate or integrate by parts, which involves differentiating also the phase function in the frequency variable. And this may pull out factors of t, which may blow up the density, the estimate that you get at the end. So we need to have a more careful look at what happens with the phase function. Here, luckily enough, we have a very explicit expression in terms of the geodesic flow. You see this term with cosine and sine, which somehow are related to the spirals that you see in the picture for the geodesics that I showed you before. And you see that this angular variable depends on time. So if you differentiate this expression in the frequency variable mu and psi, indeed this cosinus theta, sine of theta pull out factors of t, which may create problems when working with large time. So the way we deal with this problem is actually to appropriately split the sort of range where theta varies into unit length intervals, and then to somehow, so after this splitting, we do an appropriate change of variable in each of these pieces, sort of scaling and shearing in the mu variable. And after doing this kind of scaling, the t parameter essentially disappears from the expressions, and this allows us to have something which has no longer problems when you differentiate in time. So the cost that you have to, something that you have to pay, the price you have to pay is that now you have a certain number of pieces, but this is also under control. And so at the end of the day, after this additional decomposition, you get a certain number of pieces, each of which now becomes amenable to the standard Seeger-Sogge Stein argument, again, with some modifications due to the imaginary part of the phase, but then for each of the pieces, you get the expected estimate. You have the problem of summing the pieces because you get the sum blow up due to the number of pieces depends on the time parameter. But luckily enough, if one looks back at when we did the parabolic scaling, actually not only 2 to the m was bounded by the spectral parameter lambda, but 2 to the L times 2 to the m was bounded by that. And so even this small blow up can be swallowed into the parameter lambda and get the estimate that we wanted. So again, we get the estimate with the expected exponent d minus 1 over 2. Okay, so this is somehow the, in a nutshell, the idea of this proof. Let me just mention that the approach that we developed can be used, as I mentioned, in much more general situations, like Heisenberg type and even Métivier groups, and so with some adaptation, even direct products thereof. So the general setup would have a second layer, the second factor and variable u might have higher dimension, not just dimension 1. And the sort of group structure is described by a family of skew-symmetric maps depending on the parameter mu. The class of Heisenberg groups is what we discussed so far as the dimension d2 equals 1 and this j mu just being multiples of a fixed skew-symmetric matrix. The H-type situation or Heisenberg type situation is described by this condition, where mod of j mu of x is just mod of mu times mod of x. So somehow these j mu and mu as norm 1 are isometries. The Métivier condition I mentioned before is described as a perturbation of the previous one, where you just have this non-degeneracy condition, this comparability, but not exact equality. And that's why here we can also include the anisotropic situation, where you might have different eigenvalues in different directions that was not included in the H-type condition. And now, as it turns out, the previous argument can be adapted to cover the Métivier case. And one of the main difficulties there is the fact that this mu variable now becomes higher dimensional. So you cannot just do the scaling and shearing as I described before. We use the fact that mu was just 1D. Here you need to do a further decomposition into angular regions in the mu variable and then treat the transversal and radial components separately. But with some work, one can actually get hold of the whole problem and in the end get again the same result with the appropriate exponent d minus 1 over 2. Okay, so I think this more or less covers the things that I wanted to say. So I would stop here and thank you very much for your attention.
So thank you, Alessio, for a nice talk. Okay, are there some questions from the audience? Okay, yes. Okay, so I have, okay, Abhishek, you want to ask?
No, you go ahead, go ahead.
No, ask us.
Hi.
Hello.
Hi. So,
nice to see you.
Nice to see you again, yes. I have one question. So could you please explain this complex phase thing?
Yes. So let me just go back just to understand what. Okay, here. Okay, so what was the question again?
So because of the large time, the Hormander thing
Yes.
is not going to work. Because the coefficients here are not bounded. So for the Hormander thing, you need the coefficients to be C2 and bounded, right?
Yeah, I mean, to be honest, all of that we do here is about smooth coefficients, okay? So we did not ask at all the question about what happens with rougher coefficients. So our problem is not about the regularity of the coefficients. I know that there are other works in that direction which are quite interesting, but it's not what we are aiming at here. It's more about the lack of ellipticity. Now, when you have lack of ellipticity, as it turns out, what happens is that geodesics stop being length minimizing sooner and sooner, so closer and closer to the origin. So all these kind of spikes that one sees in this wavefront correspond to what are sometimes known as conjugate points for the exponential map or caustics of the geodesic flow in some sense, okay? And as it turns out, this kind of representation that was used in this kind of works using the iconal equation, and especially when you work a real valued phase function, cannot work beyond caustics. Now, this means that in the elliptic case, you still have injectivity radius. So at least for small times, you can still make sense of this. And because maybe, yes, even in the sphere case, of course, if they take too large time, then this becomes a point. And then, so I mean, the shape of of this sphere may become more complicated, but for small times, you still have a very reasonable situation. And so you can get an appropriate representation for appropriately small time. But the fact is that in this sub-Riemannian setting, if you change the initial covector, you get that the allowed time becomes smaller and smaller. And so you would not be allowed, even if you take a very small time, to get any real phase that would work, because in some directions you would hit the barrier of the conjugate point. And the crucial idea is that with the complex phase, that's what they use in the elliptic situation, Laplace-Beltrami, with these imaginary paths, allow you to cross this conjugate locus. And so that is why, in the end, this is very suitable to this sub-Riemannian setting, because it's inevitable. Here you have to cross it, otherwise you'll never get an appropriate representation. So that's somehow the idea here.
Yes. Thank you very much. And also for this complex phase, the Seeger-Stein argument works.
That's another interesting point. Actually, it was an interesting discovery for us because, of course, you need to do something. It's not exactly the same argument, but interestingly enough, this part helps in some way because actually, you see, as it is written, is plus I, but then if you multiply by I, becomes like a Gaussian decay. And so this actually can be used to have for free some additional localization. Otherwise, this term is decaying so fast that actually gives you trivially the estimate you want. So, of course, it requires some adjustments, but after that, actually, one can see that actually this fits very well into the argument, and in the end of the day, allows us to get the desired estimate.
Yes, thank you. Yes. One more question I have, maybe which is not. So, like in the Euclidean case, the moment we have estimates for the wave equation, wave operator, we know maybe results for the spherical maximal function. So, is it possible, or does there exist anything like that in this setting?
That's a good question. I mean, the point I believe is that these two problems, of course, I guess that the tricky issue here is the what is the spherical maximal function in this setting?
Yeah, I'm saying about the Korani one. So is it the geodesic maximum?
I mean, the fact is that already the Korani one is not exactly what we're talking about here, is it? Because the Korani ball is not the sub-Riemannian ball. The sub-Riemannian ball, if you wish, you can think of this guy that I showed you before, but actually, sorry, let me just find the picture. It's only the boundary would just be this first bit because the ball itself would just be inside. So in a sense, if you work with Korani balls or even with sub-Riemannian balls and you just take the boundary of the ball, you would not see all these infinitely many zigzags. So because these are actually inside, a distance strictly less than 1, it's just that you are using the wrong geodesic to reach them. And so it's no longer length minimizing. And that's why at the end of the day, I'm not convinced that there is a so direct relation unless you start using more geometric kind of objects like that. But then it depends, of course, of the kind of problem you are interested in. As you know, I mean, I guess there are other kinds of spheres like the spheres in the horizontal directions only, which of course lead to another kind of geometry. And so, I mean, then the problems become perhaps not so connected as they could be.
Yes. Thank you very much. Thank you.
No worries.
So are there any other questions from the audiences? Okay, so one thing actually, the problem which we are studying here, open in diametric spaces or symmetric spaces, or is there some work has been done?
So, I mean, I'm not aware of many results in that direction. So, what for sure, I mean, let me point this out that when you work in these exponentially growing situations, in many cases, this result that I mentioned about even Miklin-Armando type multiplier theorems may fail because you need some analyticity of the multiplier in order to get the boundaries on LP for P different from 2. On the other hand, there are some special situations, certain Laplacians or sub-Laplacians on exponentially growing manifolds, which may be, say, the hyperbolic space, but not with the sort of standard Laplace-Beltrami operator, rather with the different version, which is related to right invariant measure instead of the left invariant measure, for which you can indeed reproduce Miklin-Armando type results despite the exponential growth. And in that setting, for example, I am aware of a result by Müller and Thiele in this AX plus B group setting, effectively, where they actually get results of Miyachi-Peral type with a sharp exponent despite the exponential volume growth. But again, all these results, as far as I am aware at the moment, at least seem to be very much related with very symmetric situations where you have a lot of knowledge about the general setup. So, of course, there are variants of this setting I mentioned of AX plus B groups, also with sub-Laplacians instead of Laplacians. There are theorems of Minkling-Normander type with the topological dimension instead of the homogeneous dimension, even in that context. And so it would be very interesting to study also the wave equation in that setting. But yeah, that, I mean, to me at the moment seems to be a bit challenging with the technology that we have at hand. But of course, that also will be very interesting, I believe.
Okay. So are there any question from the audience?
Yeah, one question that you have mentioned that multiplier result imply the wave equation boundedness.
Mm-hmm.
Is the other way also true?
Yeah. I mean, of course, you have to put some assumptions, but heuristically, at least, just to mention, if you know the sharp result with d minus 1 over 2 for the wave equation, then by sort of, you take any function, you write in terms of, you subordinate it by using the Fourier transform, and then from the d minus 1 over 2 result for the wave, you get the d over 2 result for the multipliers. So actually, you need to get the better result for the wave if you want to get the sharp result for the multiplier with d over 2. So in a sense, these results imply the multiplier results with d over 2, if you have the d minus 1 over 2. Whereas if you start with the d over 2 result for the multiplier, I guess you only get d over 2 for the wave, so you are still missing the 1/2.
Yeah, okay. Yeah, thank you.
No worries.
Okay, any other questions? Okay, if there are no more questions, let us unmute and thank the speaker for a nice talk. Okay.
Thank you very much.